In the early days of AI coding assistants, developers relied on vibe coding, treating large language models like casual conversational partners through ad hoc prompting. But as codebases scale, this informal approach yields diminishing returns. An unstructured dialogue log quickly degrades into context hallucination, rule ignorance, and severe developmental drift. When an autonomous agent writes correct logic that fails to compile, or refactors a file but breaks downstream dependencies, developers frequently blame the model's intelligence. But raw capability deficits are rarely the culprit. The actual point of failure is a strict breakdown in alignment between human intent and machine execution. Delegating complex tasks requires securing 6 hierarchical layers of operational alignment. You need workspace alignment to configure the physical environment, task alignment for objective clarity, and action space and action set alignments to strictly bound the tools the AI is allowed to use. Finally, coherence and outcome alignments ensure the final code fits the broader system architecture. If a single layer misaligns, the resulting code degrades the project. To maintain reliability, engineering teams must stop interacting with these models as chat interfaces and begin orchestrating them as deeply bounded, programmable pieces of infrastructure. The primary bottleneck in agentic engineering is the mathematical reality of context windows. Frontier models possess massive capacities, but their attention mechanisms are fragile. When a model is force-fed entire codebases and global parameters, it suffers from instruction dilution. The system can only concurrently balance roughly 150 to 200 distinct instructions before it starts selectively ignoring critical rules. This cognitive saturation leads to a well-documented phenomenon known as the agent dumb zone. Once the active session's context usage crosses a strict 60 to 70, the model's attention mechanism only processes the specific rule if the active task explicitly triggers the conditional logic. By fencing off irrelevant instructions, the system actively prevents unnecessary context consumption. This preserves the agent's highly constrained operational budget, saving its logic and reasoning capacity entirely for the execution of the immediate code. To circumvent the need for massive, complex prompts, modern agentic repositories utilize a modular orchestration pattern. This is the architectural triad: commands, agents, and skills. At the top of the hierarchy is the command. Commands are user-invoked prompt templates saved directly into Git version control. Rather than typing out exhaustive instructions every time a developer wants to run a code review or generate analytics, they trigger a standardized command file that instantly injects the precise parameters into the active session. Crucially, commands do not execute logic. In a standard data retrieval workflow, the central command processes the user's input, standardizes the formatting, and then delegates the actual work by invoking a highly specialized subagent. By relying on predefined commands for workflow routing, engineering teams eliminate the variability of human typing. Repetitive tasks become fully standardized, ensuring the primary entry point for complex code execution is completely deterministic. The command hands the task off to a subagent. These are autonomous actors defined by strict YAML front matter, and they do not share memory with the main session. They are launched into a fresh, completely isolated computational context. The YAML configuration enforces strict boundaries. By explicitly restricting the subagent's tool access to a single read protocol, the system guarantees action space alignment. A data fetching agent physically lacks the capability to overwrite local files or execute arbitrary terminal scripts. Once isolated, the subagent pulls in specialized knowledge modules known as skills. Instead of flat text files, skills are formatted as comprehensive folder structures to protect the limited context window. This enables progressive disclosure. The subagent reads the top-level index file first, mapping the available documentation. It only queries the deeper subdirectories and code examples if the immediate technical parameters demand it. After utilizing the skill to successfully pull the required external metadata, the subagent returns the isolated variable back to the parent command and instantly closes its context window. With the required data secured, the central command wakes back up and invokes a secondary, completely distinct output skill to write the final file artifact to the local disk. The agent interfacing with the external internet never touches the agent formatting the local files. This rigorous physical separation of concerns minimizes security risks, prevents cross-contamination, and drastically reduces the cognitive load placed on the underlying model. Tactical state management stabilizes the code, but developers must also select the appropriate computational tier for the execution itself. Microtasks requiring 3 to 5 minutes of implementation are handled immediately with default prompting, but executing raw code directly for moderate to high complexity objectives creates directional drift. These tasks require activating a dedicated plan mode to force the AI to read dependencies and output a sequential strategy for human verification before a single line of code is altered. This chart compares the escalating architectural modalities available in Claude Code. Moving from left to right, as the objective requires richer review and parallel exploration, developers must match the prompt execution to the correct tier, capping at the highest level of orchestration. For maximum complexity, the system utilizes a cloud-first approach. By initiating UltraPlan, the compute-intensive drafting phase shifts from the local machine's terminal to external servers. The AI explores dead ends and discards hypotheses remotely, while the local environment remains untouched. Once the architectural specification is drafted, reviewed, and approved via a web interface, the finalized execution sequence is teleported back to the local command line interface. By physically separating the research phase from the execution phase, the local terminal remains pristine. The final coding agent operates from a completely clean slate, entirely undiluted by the cognitive pollution generated during the planning process. Traditional workflows require exhaustive product requirements documents up front. The Agentic framework discards this, utilizing the interview protocol with a minimal one-sentence goal. The user explicitly instructs the model to aggressively interview them. By interrogating the human, the AI autonomously uncovers edge cases, timeout strategies, and logging preferences. When the model inevitably generates code that functions but is structurally inelegant, developers often try to fix it through a long series of incremental prompts. Patching code this way guarantees deeply fragile architecture and convoluted control flows. The documented best practice is to scrap mediocrity entirely. Developers issue a strict directive. Knowing everything you know now, scrap this, implement the elegant solution. This violently discards the active branch and forces the model to execute a top-down rewrite, utilizing its now complete understanding of the problem space. To prevent project-specific knowledge from evaporating when a session ends, developers implement hooks. These act as invisible middleware, intercepting lifecycle events to run automated scripts outside the primary agentic loop. A dedicated stop hook triggers the moment a session closes. It forces the model to analyze the completed work, extract the specific architectural patterns that were successful, and append them to a global coder patterns file. The next session automatically ingests this file upon startup. After 100 sessions, the AI actively skirts the mistakes it made previously. These tactical interventions share a distinct mechanic. They reverse the traditional dynamic. The machine is forced to actively interrogate the environment, validate its own logic, and catalog its learnings, rather than passively executing human assumptions. An isolated coding agent is useful, but the ultimate goal of agentic engineering is to establish the AI as a persistent node that reliably interacts with broader enterprise systems. The standardized bridge for this is the Model Context Protocol. MCP servers bypass the need to write custom API integrations for every piece of software. By configuring standard JSON files, the coding agent autonomously and securely queries live databases, manages GitHub pull requests, and physically inspects the DOM via Chrome DevTools in real time. The community packages these capabilities into distributable plugins, seamlessly bundling subagents, skills, and MCP servers into single, version-controlled modules. This extensibility framework enables the model to function as a scalable deployment suite, allowing it to interact safely with production infrastructure. Transitioning a codebase to an autonomous framework does not require superhuman AI reasoning. Mastering agentic engineering is entirely an exercise in strict state isolation and managing the cognitive boundaries of the model. By ruthlessly enforcing global limits, splitting tasks among restricted subagents, and leaning on memory hooks, teams mathematically mitigate the risk of hallucination at scale. In the immediate future, the competitive advantage belongs to the engineers who stop writing conversational prompts and start building resilient programmatic infrastructure around their AI.